Alright guys, your essential question for today is, how do we evaluate limits analytically? First of all, the most easiest and most useful ways to evaluate a limit analytically is something called direct substitution. And just like that word implies, it basically means that you are going to directly substitute that value into your function and then evaluate it. And that's what these notes are saying. It says if you can plug C, and that can be any number, into f of x, and it generates a real number answer in the range of f of x, then that generally implies that the limit exists, assuming that the function is continuous at that point. For example, let's say that I want you to find the limit of x cubed as x approaches 2. Well, I know that x cubed is a cubic polynomial function. If you remember, the cubic function looks just like this. Now, the cubic function is continuous for all values of the domain, so that means that I can try direct substitution here, and if I generate a real number answer, then that implies that the limit is that value. So if I plug in 2 into my function, I'd have 2 to the third is 8. And so the limit of x cubed as x approaches 2 is 8. So the main thing with the direct substitution is, as long as you get an actual real number answer, which means you cannot get imaginary numbers, that's the wrong, and you can't get an undefined situation, where you have a 0 in the denominator of your fraction. And we'll talk more about that later. For right now, we're just going to go over some properties of limits and direct substitution. Alright, so just like properties of expressions, algebraic expressions, there are properties of limits as well. And I'm just going to go ahead and take a look at some of them. Alright, it says let b and c be real numbers, let n be a positive integer, and let f and g be the functions with the following limits. It says let the limit of f of x as x approaches c equal to L, and let the limit of g of x as x approaches c equals to k. Then here are some properties of those limits. First of all, if you have a constant function, remember, a constant function is one that just continues indefinitely for some value of y. If you have that, a limit of some constant function as x approaches c, it doesn't matter what that point is, what that c is, it's always going to be b. For example, let's say that I wanted you to find the limit as x approaches 100 for the function 5. Well, the function 5 is 5 all across the domain. So the limit as x approaches 100 of 5 is just 5. So the limit of a constant function is simply just whatever that functional value is. Alright, the limit of x, if you have the limit of x as x approaches to c, then by direct substitution you plug in c for x and you get c. So for example, if you wanted to find the limit of x as x approaches 5, then that would be 5. If you wanted to find the limit of x as x approaches 10, then the answer would be 10. Alright, if you want to find the limit of a power of x, like for example the limit of x to the nth power as x approaches c, then you would simply plug c in for x, and then that would be c to the nth power. That would be your answer. So for example, if I want to find the limit of x cubed as x approaches 2, just like the example a while ago, this would be 2 to the third, so that would be 8. And then finally, a scalar is any type of number that's in front of your function. If you have a scalar multiple, like b, you can actually pull that or factor out that scalar multiple. So for example, if you wanted to find the limit as x approaches 3 of 4x, then I could pull this 4 out in front, and so that would be 4 times the limit as x approaches 3 of x, and then using this property, the limit of x, plug in 3, and you'd get 4 times 3, so you'd end up getting 12 for the limit for that. Or you could just do direct substitution originally right here as well. If you plug in 3 into here, 4 times 3 is also 12. So those are just some of the properties of limits. All right, let's go over a couple of more. Um, this is very important, properties of limits. Basically what it says is that if you have a limit, a combination of limits, like for example adding or subtracting two limits, you can basically split those two functions apart. It's just no different than if you had 2 plus x, so the limit of f of x plus g of x, you can split it up into the limit of f of x plus the limit of g of x. Same thing with the product and the quotient. The only issue with quotient is that you cannot have a 0 in the denominator, and then the same thing holds true for powers. Alright, so those are really your 8 fundamental properties of limits, and we're going to use those properties to help us solve some examples. Let's take a look at my first example. Alright, it says let the limit of f of x as x approaches 5 equals to 4, and let the limit of g of x as x approaches 5 equals negative 2. Find the following limits. Let's start off with number 1. Alright, it says find the limit of x, find the limit as x approaches 5 of f of x plus f of g, 5 of g of x. What I can do here is that I can split this apart using that properties of limits that we just talked about. So this will be the limit as x approaches 5 of f of x plus the limit as x approaches 5 of 5g of x. And then also I see that this scalar right here, I can pull that out in front of there so that I'll have limit as x approaches 5 of f of x plus 5 times the limit as x approaches 5 of g of x. And now the reason why that's important is because if you go back and look, the limit of f of x as x approaches 5 is 4. So that means that this is 4. And then the limit of g of x as x approaches 5 is negative 2. So that means this is negative 2. So I would end up getting 4 plus 5 times negative 2. So 4 minus 10. So that would be negative 6. Alright, let's take a look at number 2. Again, I can split that apart into the limit as x approaches 5 of f of x times the limit as x approaches 5 of g of x. The limit for f of x was 4. The limit of g of x was negative 2. 4 times negative 2 is negative 8. And then for number 3, I can split this apart into the limit as x approaches 5 of f of x over the limit as x approaches 5 of g of x. So that would be 4 over negative 2, which would be negative 2. So you see you can use the properties of limits to help you find more complex problems. Now, again, one of the most useful and easiest ways to evaluate a limit is something called direct substitution. Now, the reason why direct substitution works is because of those properties that we just went over, or just covered. Let me show you an example of why. Let's say that I give you this problem. Evaluate the limit as x approaches 2 for this polynomial. Now, since I told you that direct substitution is valid and it works if you get a real answer, then obviously what we could do is we could plug in 2 for x and then work it out. But instead of doing that, I'm actually going to show you how the properties of the limits actually shows why direct substitution works. So what I'm going to do is I'm going to use those properties of limits. So I'm going to split this apart. So I'm going to have the limit as x approaches 2 of 2x to the 5th minus the limit as x approaches 2 of 9x cubed plus the limit as x approaches 2 of 3x squared minus the limit as x approaches 2 of 11. And then I see that there is a scalar, so I'll pull that out. There's a scalar there, I'll pull that out. There's a scalar there, I'll pull that out. But this is a constant, and if you remember the properties of limits, the limit of a constant is just that constant. Okay, so I'm going to have 2 times the limit as x approaches 2 of x to the 5th minus 9 times the limit as x approaches 2 of x cubed plus 3 times the limit as x approaches 2 of 2 squared minus 11, because the limit as x approaches 2 of 11 is 11. Alright, the properties of limits says that if you have x to a power, you can just plug in 2 and raise it to the power. So I'm going to have 2 times 2 to the 5th minus 9 times 2 to the 3rd plus 3 times 2 squared minus 11. 2 to the 5th is 32 times 2 is 64. 2 to the 3rd is 8. 8 times 9 is negative 72. 2 to the 2nd is 4 times 3 is 12 minus 11. 64 minus 72 is negative 8, plus 12 is 4, minus 11 is negative 7. And what's ironic is that if you would have simply plugged in 2 to begin with into that polynomial, you would also get negative 7. And so the direct substitution isn't, the reason why direct substitution works is because of those properties of limits. So just to show you again, okay, now let's talk about direct substitution. Now that we have proven that it's there because of those properties of limits. Direct substitution is a valid analytical method to evaluate the following types of limits. First of all, you can do direct substitution on any polynomial function. Secondly, you can do direct substitution on any rational function with one stipulation: the denominator cannot equal to 0. And then you can also do direct substitution on radical functions where your root is a positive integer. The following limit is valid for all values of c if n is odd and only c is greater than 0. In other words, you can't, again, you have to end up with a real answer. You can't end up with an imaginary answer. So that's why that stipulation is there. So if you do direct substitution and you end up with a non-real number, then you've got an issue. You can't do direct substitution for that. You're going to have to do some tricks to it, and we're going to learn those tricks as we go. Alright, a couple more rules. Direct substitution also is valid whenever you do function composition. So if you remember Fogg and Goff and stuff like that, that still applies. And direct substitution is able to work when c is a real number in the domain of your trig functions. So all of your trig functions, they also, as long as you get a real answer, you can do direct substitution on that as well. Alright, let's take a look at 3 more examples. Alright, where'd it go? Alright, for this example, it says find the limit of g of f of x as x approaches 5 if f of 5 is 10, f of 18 is 3, g of 5 is 18, and g of 10 is 2. If f and g are continuous functions. Alright, now I know that's a lot to look at, so I'm just going to look at what the problem actually wants us to find. It wants us to find the limit of g of f of x as x approaches to 5. Now, I'm just going to go back and remind you about the properties that we just saw right here. It says if you have a composition of functions, you basically can pull out that f in front of the limit of g of x as x approaches c. So I'm going to use that property now to do this. So I'm just going to rewrite this with the g out in front. So g of the limit as x approaches 5 of f of x. Now the reason why I rewrote it like that is because the limit of f of x as x approaches 5 is 10, right there. F of 5 is 10. So that value is going to be 10. So that is g of f of 5. So that would be 10. And then g of 10 is 2. And so 2 would be my final answer. Alright, let's take a look at another example. Alright, for this one, let's say I want you to find the limit as x approaches 3 of x minus 2 over x plus 6. I'm going to try direct substitution, so I'm just going to plug in 3 into that, and that'll give me 1 over 9, and so that would be my answer. You notice I did get a real number answer. So there's nothing wrong with using direct substitution. So that will be my answer. All right, let's take a look at one more. All right, let's say I want you to find the limit as x approaches 2 of x squared minus 4x plus 4 over x squared minus x minus 2. So if I do direct substitution, I'm going to have 2 squared minus 4 times 2 plus 4 over 2 squared minus 2 minus 2. Well, if you work this out, you would end up seeing that you end up getting 0 over 0, which is undefined, and more importantly, it's called something indeterminate form. And so this, when this happens, unfortunately, direct substitution in this case fails. Because remember, in order for you to be able to use direct substitution, you've got to be able to end up getting a real number answer. You don't in this case. So that means that we're going to have another method or another way of solving problems whenever you end up with indeterminate form. But the key thing I want you to take from this lesson is that as long as you, when you do direct substitution, you plug in that value and you get a real numerical answer, then that is the limit for that function. All right, that's it for today. Have a good one.